An ideal gas is transformed from state A to C according to the pressure volume diagram below, and we're told to assume that 80 joules of heat flows into the system, and the work done by the system is 35 joules when transformed along path AB. So what we have is 80 joules of heat going into the system. Now part A asks us to determine the work done by the system along path BC. Well, as we can see, there's no change in volume along path BC, so the area under this straight line is 0, and therefore the work done is 0. So we have a constant volume, so it's an isochoric process. Now if the system state returns from C to A along the isotherm AC, we're asked to find the change in internal energy. Well, for an isothermal process, the temperature does not change, so therefore the change in internal energy from C to A along the isotherm is 0. Now if the surroundings do 15 joules of work on the system along the isotherm, we're asked to determine the amount of heat added or removed from the system. Well, therefore delta U along the isotherm is 0 according to B, and that's equal to the heat plus the work done on the system. So we have 15 joules of work positive, which is done on the system, so therefore the heat is going to be equal to minus 15 joules, and because this is an isothermal compression, heat must have been removed from the system to keep it at a constant temperature. Now part D asks us to find the work done over the entire cycle ABC, and is the net work done on or by the system? Well, the work done along path AB is equal to minus 35 joules, because it's the work done by the system on the surroundings, and the work done from C to A is equal to positive 15 joules according to part C. So therefore the work done over the entire cycle, so from A to B to C and back to A, is equal to minus 35 plus 15 or minus 20 joules. And therefore the total work is done by the system on the surroundings, and it's equal to the area between these curves. Okay, so note that we had an isobaric process here, so the volume expands, so we get work done by the system along AB, and the work done on the system is given by this isotherm, so the area under the line AB is greater than that along AC, and therefore we're going to get the net work being done by the system. So have a think about that. Now for part E, we're asked what is the heat flowing in or out of the system along BC. Well, throughout the entire cycle, the change in internal energy from A to B to C and back to A for this cyclic process is 0, and that's equal to the net heat plus the work. So what we get is 0 is equal to Q net, and we had the work done by the system according to D, which implies Q net is positive 20 joules. So the system gained 20 joules of heat. Now Q net is equal to QAB plus QBC plus QCA. So along path AB, we were given in the problem that 80 joules of heat flows into the system. Along the isotherm, we calculated that 15 joules of heat goes out of the system. And given that the net heat is going to be positive 20J, which is going to be going into the system, so therefore we have 20 joules minus 80 plus 15 is equal to QBC which gives QBC is equal to minus 45 joules. So that means heat was going out of the system from B to C. And this makes sense because we have a constant volume process and the pressure drops, doesn't it? So therefore heat must be going out of the system. And I'll see you in the next video.